Okay, so we're going to do this whole problem together now. So at Einstein Technical University, data on engineering majors was collected. We saw that there were this many engineering majors and this many other majors. So they have it already in what we call this two-way table. What I'm going to do is I'm going to add up the columns. So my engineering majors, I have 30 and I have 6. So that means there are 36 total people that were engineering majors. The other majors, there's 170 and 34. So when I add that together, I get 204. Now the other part of the two-way table is that these students either lived off campus or they lived on campus. So 30 and 170 lived off campus, so that's 200 total students living off campus. And 6 and 34 live on campus, so that's 40 total living on campus. These two rows and columns should add up to the same thing. So there are 240 total students. So what's the probability of a student living on campus at Einstein Technical? Well, we look at the on campus, there was a total of 40 living on campus out of the total number of students, which was 240. So that means that my probability that a student is living on campus is 40 out of 240, or 1/6. Okay, now we want to shade the cells that are engineering majors. So I'm going to go and I'm going to highlight just the engineering majors. So those are my engineering majors highlighted. What is the conditional probability of a student living on campus given that you know they're an engineering major? So what this is saying rather than my full sample space, I want to narrow it down to just the engineering majors. And I want to know what's the probability that just out of those students they live on campus. So we're going to say the probability of on campus given that you know they're an engineering major. Well, now instead of the 240 students, I'm just narrowing it down to the engineering majors. So my total sample space is 36. So instead of being over 240, now it's going to be over 36. And how many of them live on campus? 6 of them do. So in this case, it's 6 over 36, which if I reduce it down, I get 1/6. Okay, so that is the conditional probability. I know that they're an engineering student. What's the probability they live on campus? So that's the conditional part. Now we come to being associated or being independent. So two events are independent if you know that knowing that B occurred does not change the probability of A occurring. So are these two events independent? Well, if I take a look at this, what's the probability that a student lives on campus? That probability is 1/6. What's the probability that a student lives on campus knowing that they're an engineering major? That probability is also 1/6. So knowing that they're an engineering major didn't change the probability at all. That means that they're not affecting each other at all. So that means they are totally independent. So that's how we figure out if two events are independent or if they're influencing each other. They're not independent. We don't call it dependent. We would just say they're not independent, or we would say they are associated. One is influencing the outcome of the other. It's changing the probability. Two events are mutually exclusive if they can't both occur at the same time. So for instance, you can't live on campus and off campus. You're either going to be one or the other. You can't be an 8th grader and a 9th grader. You might be an 8th grader taking 9th grade classes, but you can't be in both grades at the same time. So those are examples of things that are mutually exclusive. So can you live on campus and be an engineering major? Yes. So those are not mutually exclusive. So let's take a look at another example of this. So we've got Mr. Rexinger's high school statistics class. We've got males and females, and then we've got it broken down to wearing jeans and not wearing jeans. So just like I did before, I'm going to total up the columns. So this is 12 and this is 20. And then I'm going to total up the rows, 14 and 18. And the grand total is 32. You get that by adding the row and adding the column. It has to be the same. Okay, Mr. Rexinger is playing a game with his students. He randomly chooses a student from his class roster. If the player guesses the gender of the student correctly, you get an early lunch pass. Which gender should Madeline guess to have the greatest chances of winning? Well, let's see. We've got males. The probability of him choosing a male is going to be 14 out of 32. The probability of him choosing a female is going to be 18 out of 32. Which one is higher? Female. So she has a better chance of winning if she chooses female. Now he tells her the student I'm choosing is wearing jeans. Should she stick with female or should she switch to male? So I'm going to look back. Now I know my sample space is changing. Now it's just the students wearing jeans. So let's see what the probability of it being a male given that they're wearing jeans. So probability of male given he's wearing jeans. Our sample space has changed, so it's no longer out of the 32, now it's out of the 12. So male wearing jeans is 7 out of 12, and the probability of female wearing jeans, or probability female given, you know they're wearing jeans, that's going to be 5 out of 12. So should she change her guess? Yes, now it's a higher probability that it's a male, knowing that the person he's going to choose wears jeans. So, in algebra, when we study probability, we're studying numerical variables. So you've got, hours of study time versus percent on a test. So they're things that are numerical. This chapter, we're going to be studying categorical variables. So they can fall into categories like wearing jeans or not wearing jeans, or living on campus, not living on campus. So when we were doing it in algebra, we would get scatter plots, we'd get lines of best fit, we would have numerical analysis to see if they are associated. But in geometry, because we've got categories, we can't do that scatter plot. We just look at the probabilities if you know one thing, the conditional probability. I know it's a male given they're wearing jeans or whatever it might be. The way we decide if they're associated is if they're independent or if they're not independent. So are the events female and wearing jeans associated? Are they independent or are they not independent? So we look at this. Well, the probability of female was 18 out of 32. The probability of female given that they were wearing jeans was 5 out of 12. These things are not equal. That means they're influencing the probability of the other. So that means they are associated or not independent. So those two things do have an association. Being female is influencing the probability of wearing jeans. Are they mutually exclusive? No. You can be a female and you can wear jeans, so they are not mutually exclusive.